Right. Welcome back, everybody. And we're going to be going over some problems here together for chemistry. How's everybody doing? Let's see. Who here is online and with me? Just tell me a little hi here in the comments section, the chat section, just so I can see who here is with me. All right. Hi. All right. So, all right. How's everybody doing today? A little bit cold out, but pretty nice. And yeah, my kids are getting a little crazy staying in and not being able to go out to school, not be able to go out anywhere public at all. But we're surviving. We're surviving. Nobody's sick here, so that's good. All right. Hopefully you guys are all healthy and well, not going into any public places or crazy things like that. Right. Stay at home. Go out for a hike or something. That's fine, but be safe. Right. All right. All right. Do we have live for Bible Day? Let me see. No, we don't. We don't have live stream for Bible today. All right. So, anything else? How are you guys doing? Quizzes. Your quizzes, guys. I have not graded those quizzes yet, and so just keep in mind. I'll probably get to those grading tomorrow. All right. So Thursday I'll have some time for grading and all that kind of stuff. Okay. So, any questions about chemistry? You guys, I did notice that a few of you guys already turned in the homework for tomorrow, which is fine because I have a video that you guys should have watched, and that is the limiting reagent made easy, which I wanted you guys to watch before class today. But if you haven't watched it yet, make sure you watch it. I think it's about 8 minutes, so it is critical that you guys watch that, right? Because we don't have class together, so we don't have time to go through PowerPoints and all that. Make sure you watch the video, Limiting Reagent Made Easy. The homework was not due today. It was due because we had the quiz. We didn't have time to talk about it, so the homework is going to be due. I believe I made it due Thursday. So, hey, if you did it early, you're awesome. All right? It's nothing wrong with doing something early. It is a problem if you do it if it's late. But so let's go ahead and jump into this. We never had a chance to go over the previous time's homework again because we had the quiz, and I didn't feel like doing a live stream yesterday on the same day as the quiz. So we're going to go ahead and go over those problems from the homework from last time. We're going to do that today, and then we will introduce the new stuff. But of course, some of you guys have already watched the video, so you already know a bit about limiting reagents. That's good. Okay? So without further ado, let's jump into these problems. We have 5 grams of lithium metal reacts with oxygen in the air to form lithium oxide. Write the balanced chemical equation and what mass in grams of lithium oxide should be formed. So, very important that you're able to do this. On the test, I will write the equation out. So if you forget exactly how to do that, I'll write it out. But you will always need to be able to balance it. Let's switch to black here. Okay, so we have lithium metal, which is a solid, and it's reacting with oxygen, and we know oxygen is O2 because it's diatomic. It's one of the diatomic elements. And it's making lithium oxide. So lithium oxide, because lithium, when you have an ionic compound, we know it's ionic because lithium's a metal, oxide's oxygen's a non-metal. So lithium's going to be +1, oxide is going to be 2-. So the formula of lithium oxide is Li2O. Okay? And that should be a solid because it's an ionic compound, and ionic compounds are typically solids. Now, it is not balanced. And by the way, it doesn't ask, but what kind of reaction is that? You guys can say in the comment section, what kind of reaction is that? And while you're thinking about that, let's balance it. We have 2 oxygens there, so we need a 2 out in front here to balance the oxygens. It gives us 4 lithiums, so a 4 right here. Okay, anybody? What kind of reaction is that? I'm not seeing your comments. I know there's some lag time here, but hopefully you guys got it by now. That is a combination reaction, okay? It could possibly also be a combustion reaction depending on how slow or fast the reaction is. It's combustion because you got the O2, combination because we have one product. Okay, so what mass in grams of lithium oxide should be formed? That's getting on to the stoichiometry. So this is a grams to grams type stoichiometry problem. We're starting off with grams, and we want to end up with grams of something different. Grams to grams problems are always going to be 3 steps, so 3 conversion factors. So what I'm going to do is I'm going to start off by writing out 5 grams of lithium. Remember to write the units and the chemical. That will help you keep everything straight. Okay? Write the units and the chemical. And if it's grams to grams, we have 3 steps. Now, I like to write the 3 steps all right away, but if you want, you can just write them one at a time and think about it as you go. That's fine. Okay? So, if we're starting off with grams of lithium, the first thing we want to do is convert that to moles, because the only way you can go from one chemical to another chemical is by converting it first to moles. So lithium, if you look at the periodic table, has a molar mass right there of 6.941 grams is 1 mole of lithium, okay? And the reason the grams are going on the bottom is because we're starting off with grams and 1 mole is on the top because we're solving for moles, okay? Keep in mind, very important, this 4 in front of the lithium does not get incorporated whatsoever in the molar mass. The molar mass just has to do with the chemical and has nothing to do with the coefficient in front, okay? Subscripts are included in molar mass calculations, but coefficients are not. So that's just simply 6.941 grams per mole, okay? Next, once we've got this converted to moles, we're going to go ahead and convert it from moles of lithium to moles of lithium oxide. So we're going to put our 4 Li on the bottom because we start with lithium. We put lithium on the bottom, and the 4 comes from the balanced reaction. Okay? And we're solving for lithium oxide. So that's Li2O on the top, and we have 2 of those right there. Okay? So last of all, it wants us to solve for grams, so solve for the mass. So we need the molar mass of lithium oxide. And the molar mass of lithium oxide is something that we need to calculate. So Li2O, that's got 2 lithiums and 1 oxygen. And so we know lithium, of course, is going to be 6.941 plus oxygen. You can look at the periodic table. Let me see if I can get this on the screen. Oxygen, right, is 15.999. Okay, so let's go ahead and write that down. Plus 15.999. Add that all together to get the molar mass of lithium oxide. 2 times 6.941 plus 15.999. And that's the molar mass of lithium oxide. That's 29.881 grams per mole. Okay? So that molar mass is our conversion factor between grams and moles of that chemical. And so if we have moles now of lithium oxide, we want to convert those moles to grams. And so we're going to put the thing that we're solving for on the top. That's going to be our 29.881 grams is equal to 1 mole of lithium oxide. Okay? So that's our setup here, right? Going from grams to moles, going from lithium to lithium oxide, and going from moles back to grams. When we do the math, what you're going to do is you're going to multiply by numbers in the top, divide by numbers in the bottom. So we have 5 divided by 6.941 times 2 divided by 4, or you could just simply put divided by 2 because 2 over 4 is the same as 1/2. Then finally times 29.881, or you could just use your previous answer for that. And that's going to be 10.76. And we can round that off because we have 3 significant figures. We're going to round that, put it over here. We're going to round that to 10.8 grams of Li2O. Okay? All right. So questions so far. All right, so far so good. Hopefully you guys did fine on this problem in your homework. Okay? And the second question, the question number 10, is related to that. Okay? It says we have 5 grams of lithium metal burns in air And so Burns indicates that, yeah, this is actually also a combustion reaction, so combination and combustion, and produces 7.11 grams of lithium oxide. What is the percent yield? Okay, so this, what is that called? That 7.11 is called the actual yield. That's what you actually get. Okay, and this 10.8 grams, that is the theoretical yield. It's what you should get. It's what you calculate to get. Okay, so what we're going to do is we're going to do the actual yield. So your percent yield is going to be the actual yield over the theoretical, all times 100 to turn it into a percent, which is going to be 7.11 grams divided by 10.8 grams times 100. And let's see what that gives us. 7.11. And I like to use, rather than using 10.8, I like to use the exact number in my calculator. So I just do 7.11 divided by my previous answer, and that'll get me 0.6606. And so times 100, right? You can do that in your head, or you can do it in a calculator. It gets us 66%, right? 66%. And we have three significant figures. So I'm going to round that 0.06 up to 0.1. 66.1% yield. Okay? 66.1% yield. Guys, any questions on that? That's questions 9 and 10 from the homework, which were due yesterday. But we're only going over it now. So 66.1% yield. Okay. Without any questions, let's jump on to the next one. Number 11. Balance the combination reaction between magnesium metal and nitrogen gas, and then we get all these numbers, figure out actual yield, theoretical yield, percent yield, all that kind of stuff. So nice, right? Same kind of situation, same kind of problem. But we have different numbers and different reactions. Okay, but the same setup. So we have magnesium metal, Mg, and nitrogen gas. Nitrogen gas, of course, being diatomic. And it's a combination reaction, so we know there's only one product, and if there's only one product, it's going to be magnesium nitride, and magnesium is 2 plus, nitrogen is 3 minus in ionic compounds, so it's going to be Mg3N2. Ionic compounds are typically solids, so that's going to be a solid. Okay? Is it balanced? No, not balanced. But this one's super easy to balance because nitrogen is already balanced. Magnesium, there's 3. So all we need is a 3 out there in front of magnesium, and we're good. Okay. Now, we are reacting 13.49 grams of magnesium. So the very first thing we're going to do is we're going to write that number down. This 13.49 grams. And we're going to write down the chemical. Write down the number, the units, and the chemical. Okay? Make sure you write all that down. So it's reacting with nitrogen to produce this. That 14.31 already we know that's what? That's going to be our actual yield. How do I know that? Because it's what you actually produce. So when you see things like that, when you see something say collect, produce, make, that is your actual yield. That's your hint that that's what you actually get. Okay? So back over here to this calculation. So it asks us, what is the actual yield? That's the actual yield. What is your theoretical yield? The theoretical yield we're going to use by calculating from this. If you have 13.49 grams of magnesium, how much magnesium nitride should you make if everything works out perfectly? And we're going to do that. It's going from grams of magnesium to grams of magnesium nitride. So grams to grams should be 3 steps. Typically for these 3-step problems, you're going to notice that you're going to have 1 mole in the top left and 1 mole in the bottom right. That's because you need to convert from grams to moles, and then from moles back to grams. And that's why we have this 1 mole here and 1 mole there. Right here is going to be the molar mass of this thing. It's going to be the molar mass of magnesium. And so if you look at your periodic table, you'll find that that is 24.305 grams. Okay? And then this is going to be the molar mass of magnesium nitride, which we can calculate here in a minute. But before we do that, let's look at what is this middle step. The middle step is always from the balanced reaction, and it's going from magnesium to magnesium nitride, right? Because in the end of the day, we want to get our answer in grams of Mg3N2. Okay? So what we're starting off with, the chemical magnesium must go on the bottom, right? The thing you start off with goes on the bottom, so you can cancel out. And the thing you're solving for is going to go on the top, right? And that's going to be Mg3N2. And you have only one of those because there's no number out front. All right? So the last thing here needs to be the molar mass, and this is the molar mass of this chemical right here, and this is the molar mass of this chemical right here. Okay? So let's go ahead and calculate the molar mass of magnesium nitride. So that's going to be for Mg3N2, right? We do need to include subscripts in the molar mass calculations. We do not include coefficients in molar mass calculations. So this is going to be 3 times the molar mass of magnesium. And so just bring this down here for your reference. So magnesium right over here, that's 24.305. So 3 times 24.305. And 2 times the molar mass of nitrogen, which is 14.007. Add it all up. See what we get. 3 times 24.305 plus 2 times 14.007 gets us 100.9, let's just say 3 grams per mole. Okay? That's our molar mass. Of magnesium nitride. And that is going to go right over here. Okay? 100.93 grams. Okay? So once you got that all set up, the last thing to do is do your calculation. So we need to do the calculation, and I'm going to go starting from the left. I always go from left to right. I do 13.49, multiply by numbers in the top, divide by numbers in the bottom, divide by 24.305, times 1 divided by 3. I don't need to write the ones in. And then finally, times that molar mass. I'm just going to use the molar mass I have in my calculator, so second answer. And that gets me our final answer here for that amount. That's going to be 18. And we have 4 significant figures here, right? So 4 significant figures, so it's going to be 18.67 grams of magnesium nitride. Okay? 18.67 grams of magnesium nitride. That is what? Is that my theoretical yield, or is that my percent yield? What do you guys think? What is that number? Or is that something else? That is my theoretical yield. Okay? Theoretical yield. Why is that? The theoretical yield is the amount that you should make, the amount that you could make if everything works perfectly. Okay? And so that's what we calculated. If I start off with this amount of magnesium, and this is the amount of magnesium nitride that we should make if everything works perfectly. But we know in real life, not everything works perfectly, so we get an actual yield that is less than that. And so our percent yield is going to be our actual yield of 14.31 grams divided by the theoretical yield of 18.67 grams times 100 to turn it into a percent. And let's go ahead and just do that right now. So it's going to be 14.31 divided by our theoretical yield. And that's going to give us 76.64% because we have 4 significant figures. And I'm going to round up that 5 is going to cause that 3 to round up to a 4. Okay? Any questions? I'm not hearing back from any of you guys. I'd like to hear from you guys to make sure you guys are following along all right. But that is problem number 11, okay? And make sure you check your answers as you go. If you guys made any mistakes, try to figure out where you made the mistake or why you made the mistake so that you can not make the mistake again later. It is absolutely a critical part of the learning process that you figure out where you make mistakes. Everybody makes mistakes, right? Everybody makes mistakes, and that's how you learn. You learn by not just making mistakes, because you don't always learn from your mistakes. You only learn from a mistake if you correct it. If you think about, okay, why did I make a mistake? Or how did I make a mistake? And then you correct it, okay? That's how you learn from mistakes, okay? So if you make a mistake, great, but correct it. Figure out what went wrong and see what I did, all right? So let's jump on to the last part of your homework before we go on to the new stuff for today, and that is this. Oh, this is a beautiful reaction. Very, very dangerous. It used to be done quite commonly in labs back in the day before they had portable oxygen readily available. They used to make oxygen through this reaction. Why is it crazy? It's crazy because potassium chlorate is super, super reactive, and if you have one little tiny bit or drop of some kind of impurity in there, this whole thing will explode in your face. And you might think explosions are all fun until it actually happens to you, and you have shards of glass flying at your face very, very quickly. That's not a good thing. Okay, so this is a dumb reaction to ever do in the lab because there's so many better ways to get oxygen. But potassium chlorate is fun. It's used in fireworks and all that kind of stuff. So it's a great chemical, but used for fireworks, not for making oxygen in the lab. Okay, so here we go. I have 3 oxygens here. I have 2 here, so I'm going to balance it by putting a 2 here and a 3 there. Okay, that's going to get me now 2 potassiums and 2 chlorines, and so I'm going to put a 2 there, and my whole reaction is balanced. Okay. All right. So 13. If you decompose 2.62 grams of potassium chlorate and collect 0.94 grams of oxygen, calculate the theoretical yield, actual yield, percent yield. So same kind of deal, all right? Same kind of deal. But there's only one little twist to this one. This one's a decomposition reaction rather than a combination reaction. And so we have 2 different products, and we need to make sure we do the calculation for the right one. So let's do that right now, okay? So we're going to start off with our 2.62 grams of potassium chlorate. Of course, writing down the number, the units, and the chemical. And we need a molar mass for potassium chlorate, because that's the only way that we can determine how many moles we've got. And so we're going to go back to the periodic table to do this, okay? So we've got potassium. Let me just do it right here in my calculator. Potassium, there's 1 potassium, so it's 39.0983. There's 1 chlorine, so plus 1 chlorine, that's going to be 35.453. Plus, we have 3 oxygens, so that's going to be 3 times 15.999. And that's going to be our molar mass of 122.548 grams per mole. Okay? Now, notice that when I did that molar mass calculation, that I included the subscripts in the calculation, right? That 3 times the molar mass of oxygen, but I did not include the 2. Coefficients are not included in the molar mass calculations, but the subscripts are. Okay. So, do it fast. I'm doing it as fast as I can. Thank you. So, next, what I want to do is I want to take this 2.62 grams of potassium chlorate and I want to convert that to moles. So what I'm going to do to convert that to moles is that I want to use my grams. So I'm going to start off with grams. Grams are going to go in the bottom. So it's 122.548 grams in the bottom. And I want to convert that to moles. So 1 mole is going to go in the top, right? So this is going to go from grams of potassium chlorate to moles of potassium chlorate, right? Next, we are going to go from potassium chlorate to some other product, all right? Which one? Okay. You're going to go to, and that's a good question, right? Because this is going to be a reaction where you're going from, let's see, potassium chloride to one of these products. We have a decomposition reaction. Which product are we going to solve for? And that's going to be key because when you solve this problem on a test, you want to know, okay, which product you're going to solve for. Because it doesn't tell you, but it kind of does tell you because it says right here that we collect 0.94 grams of oxygen. So that 0.94 grams of oxygen, that is our actual yield. And we want to make sure the theoretical yield is for the same chemical, okay? So the theoretical yield needs to be for the same chemical. So we're going to solve for oxygen, which means we are not going to worry about potassium chloride at all, okay? So if we're going to solve for oxygen, what we're solving for is going to go on the top. That's going to be 3O2 on the top. And if we're starting off with potassium chlorate, we're going to put 2 KClO3 on the bottom. Notice, guys, that this chemical that you're starting off with goes in the bottom here, and the chemical that you're solving for goes on the top. Okay? All right. Last of all, what are we going to do? We want to convert that into grams because we have grams of oxygen as our actual yield. We want to convert that grams to, we want to convert that moles of oxygen to grams of oxygen, and we need the molar mass to do that. Okay? So the molar mass of oxygen is, remember, we're not going to worry about the 3, but we are going to worry about that 2 for the molar mass of oxygen. That's simply going to be 2 times the molar mass of one oxygen, or 15.999, which is what? 2 times 15.999 is the molar mass of O2 of 31.998 grams. Okay? So many people make a mistake on this. So I really, really want you guys to pay attention to this and say that you're going to always include these subscripts for the molar mass calculations, but not the coefficients. That's how I know I've said that like at least 3 times this video already, but that's because so many people make this mistake. Please include the subscripts, but not the coefficients for the molar mass calculations. All right. So last of all, that's going from moles of oxygen to grams of oxygen, and we're going to do the calculation together. And that's going to be your 2.62 multiplied by numbers in the top, divide by numbers in the bottom. So that's going to be divided by our 122.5483 times 3. We multiplied by numbers at the top, divided by 2, divided by numbers in the bottom, and then finally multiplied by this molar mass of O2, which I'm just going to use the number in my calculator. And that gets me the final answer of 1.026. We have literally only 2 significant figures for this answer. So you could say 1.0, but 1.0, typically you're giving that one significant figure or giving that 2 significant figures is not very good, especially because you have a 9 here. So really we can use 3 significant figures for this one. So it should be 1.03 grams of oxygen. Okay? All right. Now that number, that 1.03 grams of oxygen, what is that? Is that, what quantity is that? What are we going to call that? Anybody? Okay, so you guys can think about that, what that 1.03 is. And then I got a question here. Why did you do KClO3 instead of doing KCl? Because we don't know anything about KCl, right? So it says 2.62 grams of potassium chlorate. Maybe that was the problem, and you didn't realize that the chlorate refers to KClO3, and the KCl is chloride. So pretty tricky there because they have very, very similar names. Okay, so we're using potassium chlorate, the KClO3, because that's what we have in the problem. We don't know how much of potassium chloride we have, right? We don't know. It doesn't say anything about potassium chloride here. Okay. All right. Okay, so I see you guys answered the question here. What is that 1.03? That's going to be our theoretical yield. finally, our actual yield of 0.94, we're going to use that to calculate the percent yield. That's going to be 0.94 grams divided by a 1.03 grams. And we're going to get something a pretty good yield here, right? Because they're pretty similar, right? 0.94 divided by, and this is key here, guys. Don't actually use 1.03 or don't use 1, right? Use the number in your calculator, because if you don't, you're going to end up with a rounding error, okay? So it's going to be 0.94 divided by 1.02614, et cetera, and that's going to get me a percent yield of 91.6%. We have kind of like two significant figures, so that's really going to be 92%. Okay, 92% there. Okay, 91.26. So it's really 92%. So we're going to use two significant figures. The only reason I gave three significant figures for this one was because we have a 1 there, and chopping it off at 1.0 would really be improper. Okay, so 92%, and we're all done with that. We have about 10 minutes left where we can go over the new stuff. Hopefully you guys all watched my video, the limiting reagent made easy. Make sure you guys do that. The limiting reagent made easy is going to go through the theory behind this. We're just going to jump into the first couple practice problems on limiting reagent made easy, and then we're going to be done. Okay? So let's go ahead and do that. We're going to skip. I'm going to skip 1 to 3. You guys can do that on your own time. You can watch the limiting reagent made easy, the video that I made. But I want to go ahead and use this time, the last remaining time, to just go through these two practice problems, number 4 and number 5. We're going to do those together, and then you guys have to do the backside all on your own. Okay? All right. So, number 4. We are reacting 1 mole of hydrogen gas with 1 mole of oxygen gas to produce water. What's the limiting reagent? How do you know? And guys, if you haven't watched Limiting Reagent Made Easy yet, make sure you watch that. And if you want, you can just go out of the live stream and come back later so that you know what's going on. But I want to make sure I solve these for you guys so you can watch how we actually solve these problems. Okay? So we have hydrogen gas, we have H2 and oxygen gas, and so you guys should be familiar with this reaction. Hydrogen plus oxygen is going to make water, right? Not balanced, so we put so that's our reaction, right? Can we go over number 5? Yeah, we'll get to number 5. That's the last thing I'm going to go over. Okay? And we have moles to moles in this one, right? So we have moles of hydrogen, and we have moles of oxygen, and we have moles of water. So this is a moles to moles kind of problem. So let me just start off with, in these limiting reaction type problems or limiting reagent type problems, you're going to want to solve 2 different conversions. So what you want to do is you want to solve, so we have 1 mole of H2, and we have 1 mole of O2. And you want to ask yourself, how much product can you make from each of those? Okay? How much product, how much water can you make from H2, and how much water can you make from the O2? Okay? And because these are grams to grams problems, they're only 1-step conversions. Okay? Only 1-step conversions. The conversion factor is going to be found right here in the balanced reaction. So if we're starting with H2, we're going to put 2 H2 on the bottom. And if we're solving for water, we're going to put 2 H2O on the top. Again, whatever chemical you're starting with goes in the bottom. The chemical you're solving for goes in the top. And if this is just 2 over 2, that's literally like 1. So 1 times 2 divided by 2 is 1. No need for a calculator on this one. 1 mole of H2O. Okay? This one right here, what if you have 1 mole of oxygen gas? Okay? If you have 1 mole of oxygen gas, we're starting with oxygen. You're going to have 1 O2 on the bottom. Because we start with oxygen, you put the O2 on the bottom, and there's only 1 here because there's no number in front of the O2. But we're solving for water. We want to know how much water we can make, so we put 2 H2O on the top. Notice that the tops of these are going to be the same. Okay? Simple math, 1 times 2 over 1 is going to be 2.0 moles of H2O. Now, here's where we need to stop and think about it, right? So, the smaller of these two numbers is going to correspond to the theoretical yield. Why is that? Let me go ahead and circle that. The smaller of these, so 1 and 2, the smaller is going to be 1. That's going to be the theoretical yield. And that's going to be the theoretical yield because once you make that, you're going to run out of hydrogen. And you cannot possibly make any more water because you've already run out of hydrogen at this point in time. Okay? So that means that 1 is the theoretical yield, and hydrogen, let me do it this way. So hydrogen, that is going to be our limiting reagent. Reagent simply means reactant. It's the reactant that limits the amount of product you can get. Okay? So the thing that's in excess, I don't know if it asked about it, but the oxygen, that O2, is in excess. Okay? So that's a moles to moles type problem. Let's go ahead and do the last one here before we're ending. And it was asking us about this last one here. So this, or number 5, so that's going to be the last problem we're going to do. We're going to do it the same way, except it's going to be a little bit more challenging because we have grams and grams. All right. So we have 77 grams of lithium, and I feel like we've already done this reaction very recently. So we have lithium metal is going to react with nitrogen to make one product. If it's one product, we know it's a combination reaction, and we know it's lithium nitride. So lithium nitride, the lithium is a positive 1, nitrogen is a negative 3, which means our formula of our product is Li3N. Okay? So our reaction is not balanced, so make sure you balance it. Very, very important. If you don't balance the reaction, everything else will be wrong. If you have 2 nitrogens here, you need to put a 2 out in front there. It gives us 6 lithiums, so we put a 6 there. Okay? Next, we have to look at this. We have 77 grams of lithium, and we have 55 grams of pure nitrogen. And we have 88 grams of product that is formed. So we have a whole lot of numbers. What do we do with this? Okay? The 77 and the 55 are the numbers that we're going to use to do the calculation. The 88 grams of product is the product that is formed. So this 88 grams, we know that is our actual yield. So wait to use that. Don't use that until the very end when we calculate the percent yield. Okay? We are going to use the 77 and the 55 in calculations. So let's go ahead and do that. So we have 77 grams of lithium, and we have 55 grams of N2. And in this calculation, because we're starting with grams and ending up with grams, they're both going to be 3-step conversions. Okay? They're both going to be 3-step conversions. And then we're going to compare the two answers, and the smaller of the two will be the theoretical yield, and the reactant that makes the smaller amount will be the limiting reagent. And we can't just look at these numbers and say, oh, wait, 55 is smaller than 77, so therefore nitrogen is limiting. No, you can't do that. You have to actually look and see how much product they form. So let's do that. For these setups, typically, you're always going to have 1 mole in the top left, 1 mole in the bottom right, 1 mole in the top left, 1 mole in the bottom right. Lithium here, we want the molar mass of lithium. You get that directly from the periodic table, which I can't fit it on here. That's going to be 6.941 grams for the molar mass of lithium. The middle step goes from lithium to the product, from the reactant to the product. So we start off with the lithium, 6. Lithium goes on the bottom, and if we're ending up with lithium nitride, our 2, Li3N, goes in the top. The last part will be the molar mass of that. Okay? So lithium nitride is 3 lithiums, so that's 3 times 6.941 plus 1 nitrogen, which is 14.007, gets us a molar mass of lithium nitride of 34.83 grams. Okay? Let's go ahead and set this bottom one up before we even solve that one, just so we can see how this works, so we can compare the two. Okay? Right here is going to go the molar mass of nitrogen, which is N2, so this is going to be 14.007 times 2, or 28.014 grams. Okay? And what about right here in the middle? We're going to go from moles of nitrogen to moles of lithium nitride. So if we're starting off with nitrogen, we put 1 N2 at the bottom. 1 because there's no number in front of N2. And then lithium nitride, we have 2 Li3N right there. Notice that this is the same. In fact, this is also going to be the same, 34.83 grams, right? This is the molar mass of the product. Notice that the tops, all 3 of the tops are identical. Why? Because we're solving for the same thing, right? We're solving for lithium nitride, so it's the same number and it's the same molar mass. So let's go ahead and do this calculation. Sorry, I'm going to run late a little bit, but stick with me, or you can come back later to watch it. All right. So last of all, we have 77 divided by numbers on the bottom, 6.941 times 2 divided by 6 times 34.83, and that gets us 128.8. Of lithium nitride. Okay? Next, we're going to do the same thing for the bottom one. We start off with 55, divide by numbers in the bottom. Times 2 times 34.83. And we get out 136. We'll just round that up to 8 grams of lithium nitride. So we need to pause here and just think about, okay, what does all this mean? Okay? What do these different numbers mean? Okay? This is the amount of lithium nitride that 55 grams of nitrogen can make, and this is the amount of lithium nitride that 77 grams of lithium could make. But the smaller of these two will be the limiting, the smaller of these two will be the theoretical yield, and the reactant that makes it will be the limiting reagent. So this 128, because it's smaller than 136, this is going to be our theoretical yield. Okay? And lithium, or 77 grams of lithium, that is our limiting reagent or limiting reactant. Okay? Because this is the reactant that limits the amount of product you can make. This is the reactant that makes the smallest amount of product. Once you make 128.8 grams, you can't possibly make any more. In fact, your reaction is going to make less. Why? Because in the real world, the reactions don't work perfectly. And so our actual yield is 88 grams. And so we're going to take, finally, last of all, to calculate the percent yield, we're going to take that 88 grams divided by the theoretical yield, 128.8, multiply that by 100 to turn it into a percent. And what do we get? We get 88 divided by 128.79. Okay? And I get 68.3. 68.3%. And actually, we have only 2 significant figures. So we're going to have to round some of these answers. I kind of ignored that at the beginning. So we have 2 significant figures for all of these. So we really, really should round these. This should be rounded to, let's say, 129. And this should definitely be only 68%. 68%. And your theoretical yield is 129. Okay? So I'm not going to be big on your significant figures for this, but please make sure you make sense of this. Okay, you guys have to do the back for homework, and I'll see you guys again on Friday. No class, no live stream on Thursday. Have a great rest of your day. See ya.